Assalamualaikum warahmatullahi wabarakatuh, and hi to my students. Welcome to the next video lecture for the subgroup topic. To start with, the concept of subgroup is almost similar with the concept of subset, but this time it applies to group. For example, if I take Z4, let's say a normal group G is defined as Z4 under addition, and then we have a smaller H. This time suppose it will be Z4 star under addition. The concept of subgroup, the first condition, it must be that H is a subset of G. As it is well known, is that Z4 consists of 0, 1, 2, 3, and Z4 star is 1, 2, 3. Therefore, H definitely a subset of G. Now the question, is it a subgroup as well? The concept of subgroup lies here. H is a subgroup of G if it satisfies a certain condition. There are two tests that can be applied to a subgroup to check whether H is indeed a subgroup by this symbol of G. We have one step or two step. Let me start with the two step first because it is much more thorough, it is much more detailed. The first condition for the two-step subgroup is that number one, it must be closed in H under binary operation of G. The second one, the inverse must be in H, again under binary operation of G. Therefore, we must look first at the binary operation of G. Let us apply for this question. Definitely, we must know how to develop. For this question is a modulo 4. It is better for you to show a Cayley table for Z4 star because this time H is the is supposed to be a subgroup. Then we do a Cayley table consists of Z4 star elements 1, 2, 3, 1, 2, 3. Please make sure that when you want to do the binary operation inside the Cayley table, it must be in terms of binary operation of G, which is plus mode 4. 1 plus 1, 2 mode 4, 2. 1 plus 2, 3. 1 plus 3, 4 mode 4 is 0. 2, 0. 3, 0. 2 plus 3, 5. Mode 4 is 1. 0, 1, 3 plus 3 is 6, mode 4 is 2. Let's try to apply two-step subgroup in this manner. To answer the condition 1, it is closed in H under binary operation of G. Based on this Cayley table, the Cayley table must be correct first. As you look inside here, all the elements inside this Cayley table, is it an element in Z4 star? One can notice that 0 is not an element of H under binary operation of G. Therefore, it does not satisfy the first condition. Let's try to check for the second one, inverse. Does there exist inverse? And to have inverse, you must have identity first. Again, in this case, identity is not present, because you can try to check for the case of 1. Let 1 be an element in this H. Does there exist? The question, 1 binary operation with E is equivalent to E binary operation 1, you get back 1. When you try to check 1 binary operation with any of the element in the top here, there exists no production of 1. Therefore, you can say identity does not exist. And if identity does not exist, it also applies from the previous lecture, is that inverse does not exist. Simply because the identity is not present, as it does not satisfy 2 of the conditions. As long it does not satisfy any one of the condition, but again to check for all the properties, is that Z4 star under addition is not a subgroup of Z4 under addition. Or simply you can say H is not a subgroup of G. This time, try to do another example. Again, we try to apply by using two-step subgroup test. This time, we have Z5 star. Let's say G is Z5 star under multiplication, and Z5 consists of element 1, 2, 3, 4, and then you will multiply and then modulo 5. And let's say your H is Z3 star under multiplication, and Z3 star is 1, 2. Z5 star is definitely a group. You can verify it on your own, but this time we focus on the subgroup test. You do a Cayley table for H 1, 2, 1, 2. And then the binary operation inside here is multiply modulo 5. 1 times 1, 1 modulo 5 is 1. 1 times 2, 2. 2. 2 times 2, 4. But please do not modulo with 3. You must modulo with binary operation of G, which is modulo 5. 2 times 2 is 4. 4 mod 5 is 4 here. And let's try to apply two-step subgroup test. Again, you can see here that for the closed part, there exists one element which is not closed inside there, 4 is not an element of H under binary operation of G. And for the inverse, this time the identity exists. The identity is 1 because you can check it on your own. There, 1 binary operation with 1 you get back 1, and 2 binary operation with 1 you get back 2. Therefore, E is 1. Then we need to check for the inverse. But based on the definition of inverse is that you take an element, suppose the inverse exists, commutatively it must be answerable to the E, and this time E is 1, so we put 1 there. 1 inverse will get 1 is 1. However, if you look at the row for 2 there, here 2 binary operation with 1 is producing 2, 2 binary operation 2 is producing 4. Therefore, it will never produce 1. 2, the inverse of 2 is not exist at all. And based on this one, again, you can see that H is not a subgroup of G again. Let's try another example. This time it involves Z3 star, and I take U3 this time as H. Z3 star under multiplication, U3 also must be under multiplication. U relatively prime, okay. Z3 star 1, 2, U3, the element which is relatively prime with 3 up until less than 3, which is 1 is relatively prime with 3 because the GCD is 1. 2 is also relatively prime with 3. U3 is definitely a subset of Z3 star. And try to apply Cayley table for U3. 1, 2, 1, 2, binary operation of Z3 star. 1 times 1, 1, mod 3, 1, 1 times 2, 2 mod 3, 2, 2, 4 mod 3 is 1. Let's do the first step, which is the close in H under binary operation of G. And for the closure property, with the assumption that your Cayley table must be correct, based on Cayley table, you can see all the elements inside the Cayley table there only produce 1, 2. Based on the Cayley table, all element is in H under binary operation of G. Very clear. Therefore, it is closed. H is closed. For the inverse, again, you must identify the identity first. E is 1 for multiplication. In the Cayley table also is presentable that it is 1. That's not the point right now. You must be also able to tell me what is the 1 inverse, and 1 binary operation 1 will produce the identity which is 1. 1 inverse is 1 and 2 inverse is also 2, because 2 binary operation with 2 you get the identity which is 1. For this case, your grand conclusion, inverse exists, okay, not yet, inverse exists for every element in H inverse exists for every element in H, again under binary operation of G. Your grand conclusion will be that this U3 multiplication is a subgroup of Z3 under multiplication, or you can say just simply as H is a subgroup of G. That is the example by using 2 steps. There is also an alternative by using 1 step, but 1 step is much more shorter. However, it's a little bit more complex. Let me show you. For the case of 1 step, based on the definition on the left slide there, H is a subgroup of G if he is closed under multiplication, i.e. the operation between an element with the inverse exists in H. Therefore, it combines the closure and inverse as 1 step. Again, this time you must have the inverse first, because, okay, I write it 1 step. 1 step say that a binary operation with the inverse must be present in H. under binary operation of G. As compared to the two-step, this time you need to identify the inverse first. And the inverse for this case, just now from the previous solution, the 1 inverse is 1 and the 2 inverse is 2. Right now we need to check the binary operation. For example, in this element there is only one binary operation with 1 inverse. Is it closed in H? One binary operation with 1 is 1 and 1 is closed in H. And for the element of 2, binary operation with the inverse is 2. 2 binary operation with 2, you get 1 is also closed in H. Okay? Or I do it step by step again. I repeat again, but this time it will be okay. This time you need to have an inverse. Okay, so the next line, I skipped that one just now. It will be 1 binary operation with 1. 1 binary operation with 1 is 1 and 1 is closed in H. And how about 2 binary operation with the inverse is 2 binary operation with 2. You get 1, also closed in H. You must show for every element binary operation with its inverse. And by this manner, you can see that A binary operation with its inverse is closed in H for the case of U3 under multiplication. Again, the same conclusion. H is a subgroup of G. Doesn't matter whether you use 2 steps, which is more recommended, or 1 step, it will get the same conclusion at the end. That's all for the video lecture for subgroup. We meet again for the next video. Goodbye.